Hello there, this is NopeName. Welcome to another episode of Let's Create a 32-bit computer inside Minecraft. This episode is a bit different because I have already recorded this episode, so to say, but I really wasn't happy with it. It was probably a mistake to record right after lunch, and my brain was just too tired, and that video was simply a mess, and I decided to record another one, but we already have some changes, so before I am adding new stuff, I will show you what I have added in the recording, which you won't ever get to see. So first of all, a small detail. Some of you told me that there is a new marker entity, and I'm now using that instead of the array effect cloud. And the next thing is I rearranged the whole data pack. Previously I had this ZZ private folder with all the private stuff, but that is only useful if you are running a lot of these functions in chat when the project is actually finished, but that won't happen. So we only have the programming interface between these different subcomponents like the CPU, the program memory, RAM, and the main, how I call it, which just coordinates everything. So instead I'm going to do something like functions that are accessed from other components are simply in this subfolder here. So other subcomponents will run the function load instruction of a program memory, that's why it's here, and everything else that is not accessed by others is inside ZZ private, because in theory that folder is always at the bottom because of this ZZ. That's just my naming scheme for all my data packs. And also previously I thought that these subcomponents get a lot bigger and more complex, so I thought it would be good to have an individual setup and maybe tick function for each subcomponent. But it turned out that that's actually not the case, so I decided to move everything into main. Here's just one setup function that will add all the scoreboard objectives that we need, and create this one marker that will be used by all components, because if I'm not mistaken, we don't have to access more than one entity at a time, so one entity is enough. So that's that, and the actual new stuff is the program memory. So previously we had this additional register, and the idea was to load the current instruction into that register, so we can see that that is the one currently executed. But then I decided to handle the program memory just like these, and instead of moving the currently selected data to a new register, it's just highlighted inside the memory block, and operations are executed at that position. Okay, and next my plan was to already implement the reading inside this program memory, so we can actually load instructions from here and then tell the CPU to do that, and I want to do that before adding new instructions. Right now we only have the AND instruction, which hopefully works. Let's see. Hopefully the restructuring of the data pack hasn't broken anything. So function CPU and logic and 32. No, it still works. Okay. So the plan for the instructions is I want to keep things simple, so there shouldn't be more than 64 instructions, probably a lot less. And for 64 instructions we only need 6 bits. That's enough to show numbers from 0 to 63, which is 64 numbers. And the idea is I already have this load instruction. First of all, we get this marker entity and teleport it to the memory cell which we want selected. So one instruction or one memory cell is a 32 block lane, bit lane in this direction, and these are ordered in 32 by 32 in here in this memory. And down here, this is memory cell 0, that thing here, this lane here, oops, and that's 1, 2, 3, 4 and so on. And here we continue with 32, 33, 34 and so on, and go up all the way to 1023. So overall we have 1024 instructions which we can put into memory for our program. So to get to that location, I will show you that function later, but the idea is to get to this location. Now we have the marker entity at this position here. So if we say scoreboard player set address of a program memory to 1023, that's the last memory cell. So then if we run function program memory load position, this will teleport the entity to that location here. And now we can do stuff relative to this entity. And the first thing we are going to do is run the function read cmd. It will read the command, or to be more precise, the command ID. So maybe I should rename that, because this will only read the ID. That's important because depending on the ID, we will interpret the rest of the instruction differently. So for example, now we need the documentation, so here we have all the instructions which I will probably implement. But now we only have and here we have 3 input. So the destination register, the output register, and then the 2 source registers. So for example, we will do this register number 0 and register number 3, and store a result in register number 6, something like that. And I just noticed that maybe it's, let's see, maybe you should also be able to directly no, I think I will keep it this way. Let's see. So I'm currently thinking about whether you should be able to directly enter a value here, or if you first have to set a value of a register, for example to register 0 and 3, and after that run the AND instruction. I think that makes the program more complicated and bigger and slower, but this isn't about speed, this is more about showing how things work. And I think the best thing here is to get rid of that. So, and therefore I will also change this. This is an exception. I will think about these later. Oh no, I think I will also do that. Oops. Okay. So yeah, the idea is you first have to load the value into a register, and after that you compare them or add them together, stuff like that. Okay, that makes things easier, and that means we have to enter 3 register addresses, I think. Oops. Oh, come on. No, actually that's okay. So we have 16 registers, and to give an address to each of them we only need 4 bits, I guess, which should be enough. So let's say that the AND instruction, oops, how am I going to do it? Like this maybe? Oops, messed that up. Okay, so 6 bits each. Yep. I won't write it in hexadecimal because I think that makes no sense in this case. And I will simply start giving them numbers. And I think 0, 0 should be something special. So let's start with this. Oops. Okay. Alright, so our current instruction is AND, and it has this this ID. Right? Yes. So this tells the computer that the current instruction is an AND instruction, and then it will read these 4 bits for the output register ID, these 4 bits for the first input register ID and for the second register ID, and it will ignore the rest. We don't need that. Yeah. Okay, so now back to what we already have. So in program memory, the function load instruction, as an input, it simply gets an address inside the program memory. Then it will set the marker entity to that position, and here we have to do some math because this doesn't go from coordinate 0, 0 to 0, 1023. Instead, we have this 32 by 32 cube. So to get the x and y coordinate, and we have to do modulo 32 for the x coordinate and divided by 32 for the y coordinate. I already tried in the previous recording. I'm sorry, I'm too bad to explain why this works. If you know how modulo works, when you know what this code here does. Otherwise, I'm sorry, I'm too bad at explaining this. But yeah, after that we transformed the absolute address from 0 to 1023 into x and y coordinates, which go from 0 to 31 each. And then we simply teleport that marker entity to that position by modifying the position NBT data. 0 stands for x coordinate, 1 stands for y coordinate. And after that, since this here is not at 0, 0, but at -40 and 47 instead, we still have to do some teleportation. And just to make things clear at which position the entity is, we also have an offset of 0.5. That's why it's these numbers, and that's how that works. So after this command, we have the marker entity at the correct position, and then we run relative to the position of the marker this read command ID, which will simply read the binary number of the first 6 bits. And then we get the command ID. And now, depending on the command ID, we want to interpret the rest of this instruction. And by the way, you could do instructions with variable length. So for example, we don't need these bits here, so we could let the second instruction start right after this and so on. But that makes things more difficult, and as I said, I want to keep things simple, so we have just instructions with a static length of 32 bits and simply ignore the rest we don't need. And here all of these except for that one, but was I can't speak anymore. But holy shit, most of these instructions simply read 3 register IDs. So we can do something like that. Execute if score ID of a command or instruction, if that matches 1 to, I could actually do the rest here as well. Is it correct? Yes, I think. Have I made a mistake here? No, I think it's okay. So from ID 1 to ID 1, 2, 4, 8, 16. No, yeah, to ID 16. But we ignore this one with a special because it can also have a direct value here, or however you want to call it. I will probably redesign this stuff here. So we ignore 1, 2, 4, that's 7. So we ignore 7. Unless score ID cmd matches 7 run. And when we do program memory, that's a private read free rec IDs. Read free rec IDs .mc function. Okay, and we will also do another helper function, read register ID. So we start at this position and simply read 4 bits. Okay. Or should I do it like this? Yeah, I don't want to write it all again, but but simply for 4 bits, I think that's not worth it. That's probably not worth it. Okay. So let's start. Scoreboard players set out cmd 0 in 0 in 1. So this is the ID for output register, the first and the second input register. Execute if block white concrete and I think we have to, no, we don't have to. Okay, run scoreboard players add out cmd 1 2 4 8 1 2 4 8 and now we need the offset. So our marker entity is here, so that's 1 2 3 4 5 6 7 8 9. And now we simply repeat this for the other scoreboards. 10, 11, 12, 13, 14, 15, 16, 17. That should be it. And we ignore the rest. Okay, let's try that. And that's then already enough for this episode. Oops. Okay, register 1. Oops. Register 2 and register 8. Okay, reload. Do we have any problems? Yeah, we have a problem. Load instruction. What? Oh, function, okay. Function, so let's try again. Now it looks good. We have already set the address, I think. Function, program memory, load instruction. Code objective set display sidebar command. So the ID is 9. That's 8. That's 1. That's 9. And the input is not correct. Okay. Score player set 0 command. And if we run it again, it will set back to 0. And I already have again, I made the same mistake like last time. I have to do this relative to a position of a marker entity, of course. There we go. The output is in the opposite direction. Right? Yes. Okay. Wait a second. Yeah. Okay. 9, 8, 7, 6. 13, 12, 11, 10, 17, 16, 15, 14. The bits are read in the wrong direction. So now the output registers ID 1. This is 1, 2, 4, 8. The first input register is ID 2. And the last input register is 8, and let's change it to 9, and that's 11. Okay, now it works. The rest is ignored. If we change something here, nothing will happen. Okay, so we can already read the AND instruction from memory, and now we, which I'm going to do in the next episode, we will have a function in, I think, CPU, which will call this load instruction, and then depending on the input, it will run, for example, this function here. And maybe we actually get more than 64 instructions. No, I think, because my previous plan was to make this to make an instruction that runs an operation on the whole register, or only half of it, or 1/4, but that's too much work. I want to keep things simple. Sometimes I just have an idea and start implementing it, and then I'm like, wait a second, if I continue, this will take forever to implement everything. So let's keep things simple. There's only one AND instruction, and we can now finally load it from memory. And yeah, that's it for this episode. See you next time. Bye.